Okay, so like I said, this is our last chapter we're starting, chapter 11, which is on nonlinear system identification. We're going to do an introduction today and then go over the restoring force surface method today. Thursday, we're going to go over what's known as the characteristic nonlinear system ID method. And then next week, we will go over a method known as Cindy and another one, which is a global local approach. All right, so system identification is the process of building an accurate mathematical model of a system using data and observation. So using measurements, or in some cases simulation data if you don't necessarily understand the physics, but you can have some model that you can simulate. Or maybe you have a very high fidelity model that you want to reduce down. In that case, you can use that data to produce and do system ID to produce a reduced order model. So system ID is really important in engineering and science simply because by identifying a mathematical model for a system, we can then simulate its behavior, both for the data that we have captured through measurements and observations, as well as for cases that we may not be able to simulate or are impossible to replicate experimentally. And so some application of system identification include, first, model updating. And this is where you have some existing model that doesn't match the observed behavior. And so you want to do system identification to adapt and adjust that model so that it reproduces the measured data. And second is for control system design, where by having that mathematical model, you can now actually go ahead and design a control system for that structure. There are cases where you can use system identification as a way to improve signal processing. Fourth application is for fault detection and diagnosis. And the fifth application that I'm going to mention, although there are others out there, but the fifth is environmental modeling. And like I said, there are other applications out there. You can find them in pretty much every field of engineering and science. You'll find system identification. There are three types of system identification that we're going to want to talk about or keep in mind. The first is known as parametric methods. The second is then non-parametric methods. And the third we'll label as semi-parametric. So parametric methods focus on basically identifying parameters when you already know the mathematical structure of the system. So this is very useful when you have an idea of what the underlying physics is and you can propose a mathematical model based on what you expect it to be. And then you're simply just trying to identify parameters, values of parameters in your model to reproduce that behavior. And so a simple example, if you have a spring mass damper system or just a harmonic oscillator, you know that you can then use the standard equation for harmonic oscillators to model that system, and then all you need to do is identify the stiffness and damping, assuming you can measure the mass. And if you can't measure the mass, then you would identify natural frequency and damping ratio. And so in short, parametric methods search the parameter space. They're searching for numerical values for a set of parameters. And so a major limitation of parametric methods is that once you choose a model, that's the model you're going to use, and you can only use that model, which means that if you're missing some very important physics in that model, you're never going to be able to capture that because you're just identifying numerical values for parameters, not changing the actual behavior or structure of that model. So the non-parametric methods focus on identifying some mathematical structure of a system. And so these are used when you don't know the underlying physics very well. And in short, they're going to search the function space. Their goal is to try and produce a set of functions that models that system, which may include parameters as well. And so the major limitation that comes with non-parametric methods is often they have an increased mathematical complexity, and they can have, at times, some large computation times in terms of identifying a model. And then lastly, semi-parametric methods will combine both parametric and non-parametric models together, or methods together. This is a case where you might know some of the underlying physics. You might have some understanding of like the linear behavior, but you don't have any idea what the nonlinear part is doing. And so you guess the model for the linear behavior, and then you're just identifying parameters. But since you still don't know the nonlinear behavior, you're going to have to try and identify a mathematical structure for that. Let's see. And so, yeah, in general, many nonlinear system ID methods can be grouped into semi-parametric. Generally, there's some underlying linear behavior or linear structure, and what we want to do, and we can use linear methods to identify that. And then from there, we want to try and identify the nonlinear part and augment and improve the linear model. And then, although each step is going to differ in general, but the general procedure for system identification is as follows. We're going to start off with some kind of data collection. So obviously, if you don't have data, you can't do system identification because it's all driven based on measurements or some kind of observation that you've performed, whether that's using some experiments or a high fidelity model. Second, from there is generally some type of model selection. And this could be in the sense that you are assigning a mathematical structure or mathematical model based on what you understand of the physics, or you're doing some kind of non-parametric method to identify a model for that. The third then is parameter estimation. So once you have a mathematical model, you now want to identify numerical values for parameters. And then the fourth step is model validation. Where pretty much you want to compare your model with measurements or observations that you did not use in the identification. Data that the model has never seen before, and that's how you validate whether or not it's good beyond the identification case. All right, so today we're going to talk about the method known as the restoring force surface method. This is a non-parametric method developed by Masri and Kogi. The citation is given there. I mean, even in the title, they say it's a non-parametric identification technique. This method was developed for nonlinear single-degree freedom systems and has later been extended to multi-degree freedom systems. We are only going to look at single-degree freedom systems in this, but what I'll tell you is that for multi-degree freedom systems, you typically will apply some kind of filter to isolate a single mode of response or a single component such that you can then assume that's a single degree of freedom, and then you can apply this method that way. All right, so we're going to consider some single degree of freedom system, which has a mass m, and some arbitrary nonlinear function f of x and x dot. X is the displacement, with some force f of t applied to it. And the equation of motion is given there. We're going to make the following assumptions for this method. First, that the mass m is known or at least easily measured. What does it say? Or easily measured. It's a pretty standard assumption as far as these methods go, and it's okay. It's not really a hard assumption to meet, given that you can directly measure mass. Second then is that the force F of t is known or measured. And what we mean here is that we have a time series that captures that force. Not necessarily that we know the exact forcing function, but we have a time series component that captures that. Third assumption is that the acceleration x double dot of t is measured. So we're assuming that you are measuring the acceleration. Pretty standard thing to do in vibrations anyway, using accelerometers. And then the displacement x of t and the velocity x dot of t, we're assuming that these are either measured or you can get them by integrating that acceleration. So, or they're integrated from x double dot of t. And that process might include filtering as well if needed. So generally, we want to start with an acceleration and then integrate up into velocity and displacements if you can. One reason is that doing accelerometer measurements is very easy and cheap, typically compared to doing velocity measurements with laser vibrometers. Just for perspective, I think the cheapest laser vibrometer is in the order of 10 to 20,000, and or it might be 2 to 4,000, somewhere around there. Depends on the quality. What I've seen is like 10 to 20,000, and accelerometers range from like, well, ones that are designed for doing testing range from like 300 to maybe 2,500. So they're on totally different scales in terms of cost. The other reason is that you don't generally want to differentiate when you have numerical data or experimental measurements because that amplifies noise, whereas integrating does not amplify that noise. What it does do is introduce a low frequency error that can be filtered out effectively, and that's what we do in our lab pretty much all the time. All right, so given these assumptions, we can then go ahead and take equation 1 and rearrange it as follows. We're simply going to bring the mass times acceleration onto the other side, and then we'll get f of x comma x dot is then equal to f of t minus m times x double dot. And so, again, we've assumed that f of t is known for measurements, as is the acceleration and the mass. And as a result, we can then say that the entire right-hand side of equation 2 is known for measurements. And as a result, we therefore then know this restoring force function f of x comma x dot. So then the basic idea is that we're going to produce a 3D restoring force surface, or RFS, by simply plotting f of t minus mx double dot as a function of x and x dot. So we're plotting that restoring force as a function of the displacement and the velocity. And from there, we can then use that to identify some kind of mathematical structure for the restoring force, depending on what you're expecting there and the basic physics of it. Or you can go ahead and fit some kind of polynomial surface to it as well. And so in the Masri and Kogi paper, they used Chebyshev polynomials to fit the RFS. Here, we're just going to use basic polynomials, not special polynomials. And we're just going to demonstrate this method using examples. Then you'll do a worksheet, and then the first homework problem is on this method as well. All right, so we're going to start just with a linear oscillator, a very simple system. Equation of motion is given there with the following parameters. We're just going to simulate this response for x equals 0 and x dot equals 0 equals 1 for time from 0 to 150 with a sample rate of 100. This is all non-dimensional shown here. We're going to simulate the response, plot the displacement velocity time series and their Fourier spectrum. We'll then construct the restoring force surface and then plot the displacement, force versus displacement, and force versus velocity. And finally, we're going to fit a 2D polynomial, and we'll compare that with the exact equation to motion. All right, so here's what the response looks like. It's single degree of freedom harmonic oscillator. exactly kind of the type of response you would expect to see here. Code given right there. Here's what the restoring force surface looks like. So in this, what we have is effectively the phase portrait depicted in some three-dimensional view as well. We go down and look at the next two plots. What you'll see in the restoring force is that it's very linear. The overall trend is linear, although it does deviate from being a pure straight line. The general case is that it's linear. And if you look at the force versus velocity, you can't really get anything out of that, to be honest. I've never been able to get anything out of that. One thing you can do is plot. You can find the times where the displacement is equal to 0, and then plot the force versus velocity for those times only. And what you would find is a straight line because it's a linear viscous damping. You could do the same thing for the displacement, but finding times where the velocity is 0, and then you would find a straight line along this as well because, again, it's linear. Okay, so from here, we're going to just fit a polynomial. We're just using this fit function in MATLAB to fit, in this case, a second order polynomial in both x and x dot. And this method comes out with the following parameters, and I'm just going to comment on each of them. So first, this p00, this one is very small, so we would probably just neglect this. The second term here, this is actually our linear stiffness, and it matches exactly the linear stiffness, which it should because it's a linear oscillator and this is a simulation with no noise in it. So we should get exactly that. The damping, the second term, or the third term, this is our linear damping, which is just a little bit off. And then the rest of these terms are very small, and so we would just neglect these. When we look at the Cindy approach, we'll do sparse regression where we'll do a kind of fit like this and then reject terms that are small and then do another fitting with only the terms that remain. And then beneath that, I've plotted what the fitted surface looks like compared to the response data. And you can see it fits quite well here, which it should because it's a very simple system. All right. So the complete code for this is on the next page. And we're going to take a look at another example. In this case, it's just going to be a basic Duffing oscillator. Again, we're only looking at single degree of freedom systems here. So in this case, we've taken that single degree of freedom harmonic oscillator and then added here a cubic nonlinearity, a stiffness nonlinearity with a coefficient of alpha here. Alpha is equal to 1. The linear stiffness K is only 1/2, and that C is 0.05. We're going to simulate the response for the same set of initial conditions. In this case, we're going to start off with having an unforced case, and then we're going to look later at a forced case. In this case, we're going to simulate from 0 to 200. Again, this is still non-dimensional. Plot the displacement, velocity, time series, wave transform, and the Fourier spectra. We'll then construct the RFS and plot force versus displacement and force versus velocity. Finally, we'll fit the RFS and compare it to the exact equation of motion. We'll then repeat this for that forcing term, where we have a force of 1 and omega equals 1 as well. All right, so just for part A and B, these are the displacement and velocities shown here. You can see that there is a small amount of change in the frequency, at least in terms of the wavelet transform. It's kind of wide, a little bit wide in the Fourier spectrum. Moving on, here is our restoring force surface, which you can now see is started to bend a little bit compared to the linear case, which was just a flat surface. Here we now have some bending in it. It's a little kind of hard to see when it's just static like this, but when you plot these in MATLAB, you can rotate around and you'll see you'll get an idea for what the surface actually looks like. And if you look at the displacement versus force, you can clearly see that there is some type of smooth nonlinearity here. It happens to be exactly a cubic plus the linear term, but in general, you can see that there's some type of smooth nonlinearity. And with the force versus velocity, it is what it is. I've never found a case where you get a really interesting and clear-cut force versus velocity, except for when you consider only when the displacement is 0. That's usually where that happens. And we'll see that in the third example. All right, so we're just going to do the same thing. We're going to fit a polynomial to this, in this case, a third order in both terms. And we'll just take a look at the coefficients. So this first term is very small, so we would neglect that. The second term, that is our linear stiffness, which let's just say K here. Third term, that's our linear damping. So we have K and C. Fourth term is very small, so we'll probably just neglect that. Same with the next two terms, we'll just neglect those. And then the P30 term, that is our alpha value, and the rest of these we would just neglect, given how small they are in general.
How can we decide how small they are?
Yeah, it's a good question. So part of this involves physical intuition, I would say as well. And I'll also add that there's not really any downside to leaving those terms in as well. I mean, if they're small, they will have small effects.
Yep.
So you don't really lose anything by keeping them. So if you're not aware, then you just keep everything. If you think they're weak and not important, then you can get rid of them. For something like this system where everything is non-dimensionalized and small, then you can get rid of these. That's another thing you can do is non-dimensionalize your system, assuming you can, assuming you know something about it. If you know, for example, a linear stiffness and a low forcing regime, you have that information. You could use that as a way to non-dimensionalize these and compare their values. Yeah, some of that comes from intuition and just having an understanding what's going on. Okay. So here's what that fitted surface looks like. It matches quite well, and if you were to run the code and then rotate it around, you would see that it does actually fit quite well compared to the data. Okay, so here is part E, where we're now applying a sinusoidal force to this response, as shown here. This is just the force and the velocity, and you can see in the beginning there's some transient behavior that dies out, and then it reaches a steady state. I'm not sure you guys can see that, but I'll just briefly draw. There is a second, or probably a third harmonic right here that persists throughout the entire response, and it's most likely the third harmonic of this component down there. And of course, you can actually see them. This is our omega. This is likely 3 omega, and this is probably 5 omega. Okay, so here's our restoring force surface in this case. It's not as clean and smooth as the previous case, but it still captures this kind of overall behavior. If we plot the force versus displacement, you can now see it's very narrow, and you can clearly see there's some kind of smooth nonlinearity here. That velocity versus force versus velocity, yeah, I don't know. Again, I've never really had a case where it's easy to interpret that. So here we're just going to, again, fit a polynomial model to this. We'd probably neglect this. Here's our linear stiffness. Here's our linear damping. Neglect, neglect, neglect. Here is our alpha, and then we'll just probably neglect the rest of those if you had to decide. So going back to your question about how do we know if something's small. So one thing is that if you have like a term that is cubed, and that coefficient is smaller than a linear coefficient, like much smaller, like several orders of magnitude smaller, then that's going to be a case where that's really small and not important. That's another thing, is to consider the relative magnitudes and the kind of order you would expect for a term. All right, so on the next page, I have the fitted surface, and I've plotted two views here, the standard view 3 in MATLAB, and then another view that I thought was a little bit more useful to observe and see the actual curvature of that surface. All right, the code is included down here for how I did this. And we're going to take a look at example 3. This is an experimental system where I don't have the codes to give you. So we'll just take a look at what it looks like. So this is what is known as, again, a nonlinear energy sink, which is a broadband nonlinear vibration absorber that usually has a very small mass compared to, well, it has to have a very small mass compared to the structure. In this case, this NES was going on top of a model transport wing. The NES is actually installed up here. That's what that looks like, zoomed in. And this little guy right here, let me try doing that in Scion. This little brown mass, and this guy right here, that is the NES. All right, and so here is on the left a CAD model of this. You can see that's our little NES mass. We're using music wires. These add a smooth nonlinearity. And then because it's sliding along this guide rails or this little U-shaped bracket, we should expect there to be some type of friction as well in terms of the behavior. So one more time, this little mass here, this picture is not as blurry as the others. That is the NES, and right here and here we have some thin steel wires that act as a smooth nonlinearity. Okay, on the next page, I have here the displacement response. Actually, before we go on, I want to mention that to test this NES and to identify it using an RFS, I took it off of the transport wing and then clamped this circular plate to an optical table. So in this case, the NES acts purely as a single degree of freedom. It does not include, well, it's not on the wing, so it can't include any motion of that wing, therefore. Okay, so here is a response of this system. We applied the force shown to the left and measured the response on the right. That is the displacement response, and you can see that this is very similar to our Duffling oscillator case in terms of the behavior. Although in this case, the frequency change is much larger than what we saw in the numerical example. All right, so here is the restoring force surface for this. You can see that it's very nicely curved. To the right of that is the displacement versus force. In this case, it's almost got some type of, instead of just being a pure cubic, it's almost got some kind of dip in it, something like that. But you don't need to write that down, I'm just observing here. I did not plot the velocity, the force versus velocity, because you wouldn't really get anything out of it. But what I am showing here is on the left is the restoring force versus the displacement for the times when the velocity is 0, such that all of that restoring force is caused by the displacement only. And in this case, you can see that we're able to fit some kind of smooth nonlinearity. In this case, rather than using like a cubic or some integer polynomial, we're using n equals 3.45 in this case. So it's got a linear term and a nonlinear term, and the nonlinear term has a power of 3.45. On the left, or on the right, is the restoring force versus velocity for 0 displacement, so when the displacement is 0. And we just fit a linear viscous damping here. I mentioned there was friction. In terms of the friction, we used a coefficient of friction that is typical for the two materials that were in contact, which is steel on this ultra high molecular weight plastic, which has a very low coefficient of friction. Okay, so that being said, this is a case where we actually have some understanding of the physics. Okay, so we just saw the identification results. I'm actually going to talk about what we did and how that model was created. And so in this case, because we have some understanding of the underlying physics, we know that there's a smooth nonlinearity because we've designed this thing. We know that there's some friction and linear viscous damping. We're just going to model it as this kind of Duffing oscillator where it has a nonlinear spring with a linear term and a viscous damper and a Coulomb friction slider. Equation of motion is given to you up there. One thing which, if you haven't seen it before, is that this term right here, let me do that in different color, this term right here, this is dynamic friction, dynamic Coulomb friction. And this term right here, this is equal to alpha times the signum of x times x to the absolute value of beta plus 1. So it's the same thing as what you saw in the previous plot. So we simply just do an optimization where we optimize the restoring force from this model to match what we saw in the previous plot. And by doing that, we found that the stiffness Kr is equal to 89.0 newtons per meter. Alpha sub r, this is equal to 5.291 times 10 to the 8th newton per meter raised to the actually it should be 3.45. That beta parameter, as shown in the model above in red, this would be 2.45. The damping was 0.3988 Newton seconds per meter. That gives you a damping ratio of 0.0744. And then lastly, the coefficient of friction was 0.00988. Okay, so from there, what we want to do is a model validation. We start by taking the model we identified and using it to simulate the response that we use to do the identification. And that is what's shown here. So in black is our experimental values, red is the simulation. The left way to transform experiment, the right way to transform is the simulation. Here you can see that there is a good agreement between the two responses, which there should be because this is the data we use to do the identification. If there was a bad match here, then you would know that your model is not good. I mean, it doesn't even reproduce the data you use to identify it. So, I mean, at that point, you start over. You try a different model. But since we expect it to do well here, what we really want to know is, does it do well for cases that we didn't test or we didn't use to identify it? And so in the bottom here, I had two responses. Yeah.
What is rho?
What is rho?
Rho sub r? Or?
Oh, no, sorry, that's a zeta.
Oh, that's it.
Zeta, yeah, it's a damping ratio.
Oh, okay.
Yeah. The equivalent linear damping ratio is what it is from the linear viscous damping term. It does not account for the friction
Oh, yeah.
in it. All right, so left side is a case that is 100 newtons lower in terms of the impact force. And you can see the model does a good job here of reproducing it. Actually a really good job of reproducing that response. And on the right, we have a case where it's just a little bit, like 80 newtons above, or about 70 newtons higher than what we used for the identification. You can see it does a good job of reproducing it here. So now that you have this model, we could then attach this to our airplane, or model for the model airplane wing, and then do simulations of how the NES works and performs in terms of mitigating the response of that transport wing. That's the idea that you would do here.